Hey everybody, this is Larry. I'm doing this problem as part of a contest, so you're gonna watch me live as I go through my dots as I'm coding. There'll be an explanation near the end, and for more context, there'll be a link below on the actual screencast of the contest. How did you do? Let me know how you do. Hit the like button, hit the subscribe button, and here we go. Q4, probably of two boxes having the same number of distinct bars. So this one, I think I read through it. There's no way I possibly read this quickly, right? But I scanned it, and that's why I solved the wrong problem for the first half an hour or so. Um, but yeah, so basically, what I was trying to do was solve the problem where I think I did actually read it correctly at some point, but I had a mistaken either reduction or whatever you want to call it, but just in my head where I thought that you could narrow it down to for each bore, it has to be in bucket A or bucket B, right? And that's 50% chance of bore being in A, 50% chance of being in B, and then you just, let it be, right? Um, and I did some optimizations as a result that didn't really make sense. But the reason why that doesn't work is because at the end you need both boxes to have the same number of bars. But I did not realize this at the time. I was just doing math in a really hacky way, and I was looking at the constraints here now just to make sure that if I do DP in a weird way, I can do it. And immediately I break out my LRU cache for the something. But, but yeah, so now initially I have my indexes as A and B. I because I so index is the index of the Bohr's index. But the reason why I have it structured like this is because I just didn't like maybe I read it, but I didn't really understood it that um, bucket A of number of Bohr's in A has to be equal to the number of Bohr's in B. Uh, that's the problem. And here I just wanted to I have to look this up later, but I have to look this up later. But basically, I remember there's a way to. I thought there was a way that you can do, or in Python, there's a binomial formula, which is n choose r. Um, and there probably is, but so I'll have to look it up later. It's just that I couldn't find it at the time, so I end up implementing myself, and I spent some time debugging that because I had a typo. Such as life. Like I said, it's actually kind of a very sluggish day. A lot of silly mistakes that yeah, I don't know. But yeah, but now basically what I'm saying is if A is equal to B, we return 1, otherwise return 0, where the number of distinct things are equal to each other. And the recurrence here is just for each bore index, we try to, each bore index have 6 bores, right? So we try to put, okay, that's what happens if we put 0 bores in A and 6 bores in B. What happens when we try to put 1 bore in A and 5 balls in B, and so forth. So that's kind of my strategy here. And then I count the number of ways that you can do that, basically, with binomial function. Yeah, now I'm just writing the choice function, which ends up taking me a couple more minutes, which is kind of sad because this really should have been really quick. And I have a typo here, so there's just a lot of debugging. And I wasn't even debugging the right code. That's the kind of annoying part, is that I was debugging code that isn't, that I don't use later, is what I mean, right? Um, and that kind of wasted a lot of time for me. Um, there is a world though where this is right, or for a different problem this is right, and I would have gotten it really quickly. So sometimes you win, sometimes you don't. Sometimes you do well, sometimes you don't. Because even if I submitted now, I would have been like, well, plus the 5 minutes, but I would have been like top 10 if I finished now. So I think excuse me. So I think in theory, if I had finished now, if this was the result, because I misread or just misunderstood the shuffling, then I would have been pretty much good to go. This is wrong, of course, because I got the choice wrong because I have a typo on the choice, which is kind of really sad, because that's just like, I should have just wrote factorial. Maybe that would have been more obvious. Instead of writing 3 for loops. I was thinking of just debugging our choice function by printing it out. I was like, nah, that looks right. But it was wrong. But I thought that looked right. That's why at the time I was kind of weird. But but yeah, now I'm just debugging here, and I was like, wait, this doesn't make sense, and then I eventually figure it out. Just a lot of debugging because it's one of those blind spots where you win something enough times that you because when you do debugging, you debug the parts of the code that you think is the most risky, obviously, right? And for me, I just was like, this should be right. What is going on? Uh, and I end up spending like 2 minutes debugging something that isn't even right. Yeah, here I spotted the why it was. Oh, I spotted that it printed the wrong thing, and I was like, why is this printing the wrong thing? Like I don't understand it. And then I finally got to look at the code again. I mean, I did look at. I don't know. I keep on looking at it, but I just didn't get it. One of those days, I suppose. Ah, okay. So that took 5 minutes just debugging, which is kind of that function. So that's sad. But so the answer is wrong, and I start trying to hack around this, which is a really dubious path. But like I said, the reason why this is wrong is because I looked at each four and I thought that it could be in A and B, and here I was like, oh, shuffled uniformly at random, right? So I was like, ah, I wasted 10 minutes on the wrong problem. I think I even mentioned that. The other person, Larry, mentions it now, but oh man, I solved the wrong problem. Sad face. Um, then refreshed. I was like, oh, only four people solved it, so I actually have a good amount of time, uh, and also that it's solvable. But yeah, now I'm trying to just actually think about how to attack this problem. Uh, and unfortunately, I went down the path of like, okay, let's just count the. I knew what I wanted to do, but I was doing it in a wrong way, like logically. And what I mean by that, I was from here, I was trying to figure out like, okay, let's only count the paths that are possible, and then go down that way. It's the type of subproblems. So and that's basically what I was trying to figure out ways to kind of play around it. It's unfortunately. Yeah, I'm just and here I was just I think I was still in the mindset of hacking the current solution to make it fit. Um, yeah, and that's pretty much I think of like, okay, what if I, but at the end of the day, I did not really need to do that. I think I just need to restart. So I'm going to skip ahead. I mean, feel free to stay here or watch it on 2x or something. But all this until the next marker, read, click on the description or the timeline thing. And yeah, I'll get right back to you. But that's when I finally solved the problem a little bit better. Well, I know it's wrong. I'm done. I'm here again. But yeah, but basically what you're watching is me not giving up, but giving up on this way of solving it. I was like, okay, Larry, first principles. What do you want? What are you trying to get? What are you trying to solve? And how are you going to attack it? I said, okay, there are only 48 bars. Let's let's put it in, right? Let's just expand it out so I could write the formulas a little bit easier because I think I was getting confused at some point. And here I'm like trying to think about what I could reuse and what I could use for this problem still. But here I already, resolved to kind of restarting it. And it's remarkable somewhat. I mean, and that's the thing about grinding. I kind of keep on focusing and keep on working hard on these problems. Um, Sometimes it works, sometimes it doesn't, but you always learn a little bit more about the problem. And even though I did solve the problem the wrong way, I was able to kind of have a better understanding of a problem than I would have otherwise, obviously. I mean, I knew what not to do now, right? but but yeah. So I finally reduced the formula to instead of kind of putting together. So what I was trying to do before for 20 minutes or something like that was I was trying to combine the numerator and the denominator in a way, thinking that they're independent of each other. And there might be actually a way to do it, but my math was not strong enough to do it that way. So what I was like, okay, actually, what I'm really actually wanting to do is just count the number of ways that um, count the number of ways such that our constraint works, which we could use DP, and count the number of ways in which a looser constraint of which is a possibility but false. So basically, you have three ways of. And I was kind of thinking about it during before, but I was trying to merge them together in a way that I couldn't get it to work. But basically, what you could think about it is that each state, if you will, have three different possibilities, right? One is it could be true, meaning it is a valid end sequence, and yeah, that is a valid end sequence, and that yeah, and that's just one of the possibilities that you count positively, right? And then the second possibility is that it is false, but it still counts as a possibility of some a sequence that you can generate, except for that it will count as zero, right? And then the third is just that it's not a possible, feasible possibility. So in that case, I wrote a count which counts the numerator, which means all the good ones, all the numbers that are given to us, and then the denominator, which just counts the total number of sets that we can be possible, but even the ones that we don't want. So basically, we have the things that we want on top, and then the things that the combination of things that are possible on the bottom, and we both do a DP for that, and then we solve it that way. That's pretty much it. And the denominator, of course, is actually you could prove that to be n choose n over 2, but I wasn't thinking about it, and I was a little bit copy and pasty because you could see it because but I mean that's just the way I did it. So you may wonder why that this runs in time. The reason is that even though I have extra dimensions, and this is why it's required to do the complexity analysis, is that even though I have extra dimensions, the extra dimensions they depend on each other. So all these dimensions are not exactly independent. And because I did it top down with LRU cache, it doesn't create an entry for all the possible states. It only create an entry for the states that you visited, right? And because those visited states are not the exhaustive number of possibilities, that's how it gets it into running time. Even though that's at the time I didn't know that, I just kind of submit YOLO. So this is pretty much it. I had a So unfortunately, I have a typo that I still spent a couple more minutes to debug. So it's just a lot of typo filled day. It's very frustrating looking back because like I have the right ideas in a lot of places, not this one, but in a lot of places, but I just have the wrong idea. And this is also something that is what happens when you copy and paste. So kids don't copy and paste, but that's what I did anyway. So maybe I'm a hypocrite for that particular one. But once you do that, once I figure out the typo, I submit and it was good and I was happy. Cool. Hang out with the other Larry. He'll start talking soon, and I will see you later. Bye bye. Hang out with him. Let me know what you did. Not silly mistakes, but that's okay. Yeah, Q4 was really tricky. I solved the wrong problem in that I thought I just misread the problem for a long time, and I was trying to hack it. That if you look at my um, if you watch what I did, that's basically what I did. But basically, the problem that I initially tried to solve, and that's what's tricky about these probability questions, is that you really have to get the denominator right. So it's not because a lot of the times when you're the similar problem is you have to count, and the count is just counting, um, yeah, just counting something, and you get it's very obvious how you count because you only have these conditions, and you're trying to meet these conditions with dynamic programming. I'm hand waving a little bit, and it's not as easy as it sounds, but it's the easier version of this problem, is what I'm trying to say. Um, but for this problem, so what I thought I read was that for each Bohr in Bohr's, or each Bohr, for each Bohr, you can be anywhere. Also, that's so that means that all the Bohrs could be on the left bucket box, and all the Bohrs could be on the right box, for example. So it took me it took way too long for me to reread this problem to understand that actually it's shuffled randomly, right? Or it's shuffled uniformly. So that means that the left box has to have the same Bohrs as the right box. And I did read it at some point, but it took me, and I was unfortunately stuck in a mindset where I was trying to hack the solutions that I had into this solution, and I couldn't really get it to work, as you saw, and I ultimately did not get that to work. Maybe I could get it to work, but I don't know. Maybe my optimism was what the issue was, but what I end up doing was basically just getting the numerator and the denominator separately. The numerator, we know that it's basically just the number of counts where this is valid, where you do have where CA is equal to CB, meaning the the number of balls in both boxes are the same, and that they have the same number of distinct balls. And that's I did that with a bit mask ultimately, but you probably could have been a little bit smarter. And I also converted it from balls to labels to kind of just make it simpler for me to do this recurrence. And then the total. Actually, I mean, and I actually recognized this as I was doing it, but I didn't want to. I don't know. I was trying to save time, to be honest, so I was a little bit copy pasty. So this is actually way more states than necessary, but it's okay. It's still bounded by the same complexity because it's the same complexity as count anyway. But basically, you don't even need A and B. These are unnecessary inputs. So you could have done something like this, and basically what this is saying is, give me the total number of cases where CA and CB has the same boxes. And actually, if you might, if I had took the time to think about it, it's just N, it's just this N, choose CA or CB because they're the same. But so that's just N choose CA. But I was really trying to think from first principles instead of trying to reprove everything. Hey, what is the total number of possible moves, even in routed ones, where CA is your CP? So that's kind of how I got this recurrence from first principles. A little copy and paste before, even though that is just N choose CA. And right on that actually now that I think it through this way, it's actually kind of much easier, and I should have gotten it much faster. But part of that is that I misread the problem, and sometimes misreading or no misreading, it is very hard to let go of an approach that you're confident about, even if it's wrong. But take the time to sometimes step back and start everything from scratch. I mean, not literally everything from scratch, but like mentally from scratch. And that's what I was forced to do, and that's what I did, and that's how I solved this problem. And actually, now that I phrased it the way that I just did, it seems to be a much easier problem. But in terms of just the numerator over denominator, but the way that I started approaching it with dynamic programming, and because there is a class of problems of dynamic programming where it is a probability based, with each state having effect, like with each state being a subproblem. And here I defined it a little bit incorrectly of the DP. So, oh well, not a big deal. Let's see how I did this contest. Oh, let me analyze this first, sorry. So what is the complexity of this, right? Well, A could be up to 2 to the 8. That's what I notice here, right? B could be 2 to the 8 as well. So that's 2 to the 16. Index is 48 because that's just the sum of 6 times. That's just 6 times 8. CA could be 48 and 48. So that's kind of the complexity. Actually, that seems a little high. I guess maybe I got a little lucky with that. A lot of the states are not reachable, or something like that. Or maybe the test cases are low because if I had actually done the math, but I thought this would be good enough. But yeah, but A is basically the bit mask for all the things. So yeah, so this is all of. Let's give some variables. I could say this easier, right? N is equal to total number of balls. K is equal to number of different type of balls. Then this is just K. 2 to the K times 2 to the K times. This is 48. So these are both 48s. So actually, you could have bounded this by half just by saying that if CA is bigger than N over 2 or something like that, right? But yeah, so that's my complexity, N cubed times 2 to the K plus 1. So I am actually surprised that that passed, but that's it. Yeah, and that's pretty much my complexity. My space is similar because, or exactly the same in the big O notation because we only do uh, two constant operations for this one. But yeah, that's all I have for this problem, I think. Cool. Let me know what you think. Because this is a little bit of a tricky problem, so I might explain a little bit more. But the idea is basically the recurrence. But okay, let me recap this problem. So how do you solve this problem? The recap is just find the numerator and the denominator. The total number of possible shuffles. It requires the number of balls in box 1 and the number of balls in box 2 to be the same. So this should be just n choose n over 2, which is what this recurrence does in a really unnecessary, right? And then the number of count of boxes where they have the same number of distinct. So the numerator is the count of the number of possibilities where they have the same number of distinct balls, type of balls, right? And that's what this function does. It counts. I have this thing that counts the number of things in a bit mask, and then it just does this recurrence of okay. Let's put the ball in A. And then let's put the ball in B. And then what happens when you put the ball in A, and what happens when you put the ball in B? And then at the very end, just make it 0. Just count the number of total numbers in that result. But yeah, just want to add a little bit to the analysis of the complexity of to analyze this one. So one thing that I did not do during the contest, and I'm very fortunate that it passed. Well, it's a weird way, right? Because it's that, as we talked about, I want to reiterate. So the way that you can analyze this state, right, is that, well, how many possible things are there for index? Well, it's just 48. So it's O of n times C, where C is the max element of A sub I or ball sub I. And n is you go to the total number of balls. And k is equal to the number of distinct balls. So this complexity would be, index would be n times c. No, sorry. Index can be just n. A is 2 to the k. B is 2 to the k. CA could be n. And CB could be n, right? So on a really naive analysis, which I did, that's why I'm supplementing, is that this is the complexity, right? And you could do that, and this is just, of course, 2 to the k times 2, right? And you may wonder, how does this run in time, right? Well, it turns out, and this is the one thing that is sometimes good with top-down memorization if you do it correctly, is that you don't explore all the states. And one thing that what happens is that a lot of these states are not visited, and you wonder why. How can they not be visited? Well, the thing is that, for example, CB depends entirely on CA, right? And what I mean by that is that for every index, for every number on index, let's say, well, for every number in index is essentially equal to CA plus CB, right? So basically what I'm saying here, even though I didn't notice this at the time, I mean, I was trying to rush it a little bit too much, and I did a few things. So I didn't recognize this at the time, because usually I would have to make this optimization, but I rushed it, and I didn't even realize that was too much, because if I did that, I wouldn't have done it. And you could have easily just written, you could have optimized this by doing this minus CA, and then remove that from the input. And that would save you a little bit of space, for example. But because this is the case, the real complexity is this, n squared times 2 to the k times 2. And of course, CA is less than index, so there's some symmetry, so you can divide it by 2 or something like that for more actual time performance, like tighter performance analysis. But yeah, I just want to point out, I just want to point this out because this may look confusing. Like, wow, n cubed times this whole thing. That is way too big. And you are right. Uh, so yeah, that's I just wanted to add that so that you have another thing to add to your toolbox in terms of analysis. Anyway, back to your schedule.